Okay, so if you guys notice on Canvas, you guys should see this new unit right here, right? Unit 15, exam prep. And pretty much this is what you'll be doing during the month of April with the substitute when I am gone. So first thing we're going to click on is this schedule. So if you guys can click on the schedule, if you guys have it up already, when it decides to load, yes. Okay, it'll take you to a link. And that will take you to the schedule for until the AP test. Okay, so let me just explain very briefly what you're going to be doing. And then if you have questions, you can let me know. So March 25th is when we're going to start the actual exam prep. This is the class after the electrochem and the thermodynamics exam. Okay, and so what we're going to do is we're going to look at the 2023 FRQ, so the AP test FRQ from last year. I'm going to go over it with you guys. I'm going to have you guys practice it. I'll teach you guys how to use the answer key that they provide so you can see how they grade AP tests and things like that. Yeah. So good question. So the FRQ studies, see these right here, all the FRQs, they are going to be participation. Okay, so if you complete them and turn it in, you will get credit. Okay, and you have the answers. So if you want to be lazy and not prep for the exam, you can just copy it down and get points. However, you're kind of doing yourself a disservice as you prepare for the AP test. So there's that. Okay. Now, if you guys notice, until I leave or after the electrochem and thermodynamics exam, I have 2 class sessions with you. So we're going to go over the 2023 and 2022 FRQs together. I'll teach you guys how they score it. And basically it'll be practice. Then we have spring break, which is when I'll be gone. So have a good life, guys. And then when you come back, you will be self-studying the 2021 FRQ. Okay, this is all on Canvas already. So if you want to get a head start, you can. And then after that, on the April 10th and 12th, you'll be taking a test. And this will be graded. So if you get stuff wrong, you will lose points. Okay, so you'll be graded on the practice test. So you'll have 2 days to take the test. And then on the 16th, the answers for that will be released on Canvas. So you guys can check your answers and see what you got wrong. And obviously, you can see kind of where you're doing well and where your knowledge might be deficient. Yes. You already met her. Why does that matter to you? All right. Anyway, moving on. Okay. So we got 2019 and 2018 self-study. So same thing. And then after that, on April 24th and 26th, you're going to take another test. So 2 more tests. So 4 tests left after the next one. And then the test answers will be released and you'll self-study. Okay. And then May 6th is the AP test. Okay. And then we're done. All right. Any questions on the schedule? Yeah. So there's multiple choice. So AP test has multiple choice and free response sections. You'll be doing both. Yeah, and there's a scoring guide, so the sub will be able to do it. Yeah. Any other questions? So these will be graded for accuracy. Practice test 1 and practice test 2. So you guys do need to study for that. Okay, so before, yeah.
How many points are the practice test?
It's on Canvas already. Okay, so if we go back to Canvas, the Unit 15 prep. So let's look at this one, the optional stuff. Now, these are not going to be turned in. These are just there to help you study for the exam. So if you guys click on the test prep, it'll take you to 2 links. The first one is going to be the official AP Chem FRQ. So if you click on that, it'll take you to Google Drive and you should see all the FRQs from 2010 until last year. The only one that's missing is 2020. It's because I don't have it because that's obviously COVID year. So things were a little bit different. But we have all the FRQs from 2010 and this should cover pretty much, this should give you a good idea on what you should expect for the FRQ and what for them to look like. I also have the answer keys up there for you guys so that you can see how they are graded. And that'll let you know what you need to include in FRQs when you solve them. Yeah.
The practice test first practice?
No. This is 1 and done. Okay, so yeah, and then these are what you'll be working on in class. The tests will be 20 points each, so 40 points per practice test, so 80 points total for both of them. And yeah, that's pretty much it. Any questions on what you'll be doing until the AP test? Okay, so after the AP test, I have told the sub to give you guys 2 weeks to relax. You guys worked really hard this year, so you'll have 2 weeks of pretty much makeup days, free time, whatever you want to do. That's also because it's AP testing. So I'm gonna assume you guys have other AP tests that you guys need to study for, so you guys can work on that stuff. But then after the 2 weeks, you'll have a research project to do, and that'll be pretty much it for the rest of the year. And the sub will explain that once you guys get there. But that's pretty much what the rest of the year will look like. Okay. Any questions? You guys good? All right. I am very much looking forward to not seeing you guys again. So pretty much that's gonna be it. I will be going over these two with you guys, and that way you guys know how to study for the test. Just a reminder, the people that do well on the AP test, it's people who put in a lot of work, do a lot of practice questions. If you guys take a look at the practice problems right here, they're categorized by topic. So if there's something that you want to focus more on, you can go, and there's a lot of problems. So this other side load, like there's more than you'll probably do as you prep for the test. Yeah.
What if I got a 5 on my AP exam last year without ever doing anything outside of class?
Well, you didn't take AP Chem last year. There's tiers to this. All right. So let's continue on with electrochem. But do you guys have any questions before we do? Okay. So yeah.
Do you have the right now?
Oh yeah, I do need to explain that to you guys. Okay, so let's start with the definitions for oxidation and reduction. So let's start with oxidation. So if something is being oxidized, what is happening to it? Yeah, it's losing electrons, which means that it is becoming more positive, right? So if we take a look at this reaction up here, which compound is becoming more positive? Yeah, Cr. So chromium is becoming more positive. So this one is the one that is oxidized. So the species that's being oxidized is Cr. Okay. Okay, and then obviously, if one is oxidized, the other one is reduced. So reduction is when you are gaining electrons. And this is where you're becoming more negative, right? Because if you get more electrons, you become more negative. So if you take a look at tin, Sn is going from +4 to +2. The charge is going down. And so tin is going to be reduced. Okay, so those are the species being oxidized and reduced. Any questions on that one? Hopefully not too bad. Okay, so we talked about half reactions at the very end. So let's talk about the oxidation half reaction. Okay, so this is where we just look at the species being oxidized and we just write down what's happening in terms of electrons. Okay, so we got Cr plus, and what we're going to do is we're going to draw an arrow. And then we're going to draw or write down what it becomes for the product side. So Cr3 plus. Okay, for a half reaction, we just need to write down which side the electrons go. So if something is being oxidized and it's losing electrons, are electrons going to be part of the reactants or the products? So if it is losing electrons, is this guy going to, is it going to combine with electrons or is it going to separate from electrons?
Yep.
It's going to separate. So keep that in mind. If you have an oxidation half reaction, the electrons are products. So make sure you jot that down if you didn't know that. Electrons are products in oxidation half reactions. Yeah.
So oxidation when the charge goes up.
Oxidation, yeah, it becomes more positive. Yeah, the value becomes higher. Okay, so here, we just need to make sure it's balanced. How many electrons did Cr plus lose?
2.
2. So you just write 2 electrons for the product. And that's how you do half reactions. You're just basically writing down if electrons are reactants or if they are products. All right, so go ahead and try the reduction half reaction. I'll give you guys about 2 minutes to do that. Okay, so it's very similar. You're doing the reduction half reaction, and you just want to make sure you put the electron on the right side, the correct side of the arrow. So go ahead and try that out. So on the reactant side, we have SN4 plus. So we're going to write SN4 plus. And on the product side, we have SN2 plus. So if you take a look at it, what's happening here is tin is becoming less positive. That means tin is basically fusing or reacting with 2 electrons, and that's how it becomes SN2 plus. Okay. Make sense? Now, if you guys take a look at the two half reactions, let's do Hess's law. If we combine these together, the two electrons will cancel out with each other. And if you notice, it'll be these two, which is what we have on the reactant side, and these two, which is what we have on the product side. So if you combine the half reactions, they should always equal to the overall reaction. Okay, that's how you know you did it correctly. Okay. So if you want to jot that down, you could. If you combine the half reactions, it's going to equal to the complete reaction. Basically, the electrons are what gets canceled out. All right, so that's pretty much an intro to oxidation reduction. Do you guys have any questions? Okay, so now we're going to take a look at, this is a problem that you won't see very often on the AP test, but it's a good way for us to understand how to do stoichiometry with oxidation reduction. So we're going to go over it together. So we talked about titration in the previous unit, right? And usually that's when titration is when you add a solution of known concentration to a solution of unknown concentration to find the unknown concentration's solution or concentration. Okay. So usually in acid-base reactions, we use a color change, but we can also do that in redox titration. Okay. So I'm going to go over how to do this with you guys. It's pretty much just redox stoichiometry. So it's not too difficult. But if you guys notice right here, we have a reduction half reaction and we have a oxidation half reaction, right? So the first thing you want to do when you have these two is you want to combine them to create a complete reaction. Okay, so let's jot that down in our notes. The first step to solving this is you want to write the complete reaction. Okay, so we have a reduction half reaction right here. And we know that it's reduction because electrons are on the reactant side. We have the oxidation half reaction, and we know that because it's on the product side. And what we're going to do is we're going to combine them to write the complete reaction. Okay, now before we do that, what do you guys notice is going to be the problem with these two half reactions? What's the issue? You can't just combine them right away. Yeah, you need to cancel them out, but what's going to be the issue then? Yeah, it's not going to be balanced because if you notice, how many electrons are in the reduction half reaction? 5. How many are in the oxidation? 2. So what you need to do is you need to make sure that the electrons are equal to one another so that they can cancel out. So that's the first thing you want to do. You want to multiply both equations so that you have the same number of electrons for both half reactions. Yeah.
The 8H plus is protons.
They are protons, yes. Yeah. Does that make sense, guys? So you're going to multiply the reduction half reaction by a certain number so that the electrons for the reduction half reaction will be equal to the electrons in the oxidation. And then same thing here, you can multiply this one as well. So I'll give you guys about 3 minutes. Try that out. Try to combine the reactions together. Again, you need to multiply both of them. And then after that, we'll go over it together. Okay, so let's start with the reduction half reaction. So if you take a look at the reduction half reaction, what number do we need to multiply this by in order to balance out the electrons?
2.
Yeah, 2, because what's the lowest common multiple? 10. You want to get it to 10, right? So we're going to multiply the reduction reaction by 2. Okay, that's going to get us to 16H plus 2 MnO4 minus plus 10 electrons. Arrow. We got 2 Mn2 plus 8 H2O. Okay. Does that make sense, guys? Okay, you just want to make sure the electrons are equal. Okay, let's go to the oxidation one. Oxidation, what do we need to multiply this one by? 5. So we got oxidation times 5. That's going to get us to 5 C2O4 2 minus. Got your arrow. you got 10 CO2s plus 10 electrons. And the reason why we do that is if we have 10 electrons on the left side, 10 electrons on the right side, it's like Hess's law, we can cancel them out. And then we can combine our equation together. So the complete reaction will be 16H plus 2MnO4 plus 5C2O4 2 minus. That's a long reaction. 2Mn2 plus 8H2O plus 10 CO2. And that is your complete reaction. All right, but that's how you basically combine reduction and oxidation reaction to make a complete one. So just make sure you guys jot that down. Okay, so again, make sure you guys have this copied down because we'll need it. But let's talk about what's going on in this scenario. So this is titration. So we can kind of we already are familiar with what's going on. So it tells you that you have 50 mils of a sodium oxalate and it's poured into an Erlenmeyer flask. Okay, so basically you have a flask. It's 50 mils and you got sodium oxalate in there. Okay, so Na2C2O4. Okay, and then it tells you that you are titrating in, so you are adding a 0.135 molarity potassium permanganate solution. And basically you're just stirring it, heating it, basically making sure they react together. All right, the solution is originally colorless, so this guy's colorless, but it turns pink after 14.56 mils have been added. So once you get to 14.56 milliliters, it turns pink. And if you guys remember, when there's a color change, that means that's when the solution is completely at equivalence point. And then it's asking you, what is the concentration of the oxalate solution? So basically, the question here is asking, what is the concentration of oxalate? And it's going to be C2O4 minus. That's what you're looking for. Concentration of C2O4 2 minus. Okay, so that's what you are trying to figure out. Okay, any questions on the setup, the scenario, what's going on? Yeah, I know it's a lot of text, but that's why I kind of like drawing these pictures. It makes it very easy for us to kind of see what's going on. Okay, so the first thing that we want to do is we want to figure out how many moles of our titrate that we added. So how many moles of KMnO4 did we add into that? Now, if you take a look at it, we have molarity and we have volume, right? So how can we find the moles of MnO4 that we added?
Sorry?
How can we find how many moles of this we added?
Oh, you just plug into the bowl.
Yeah. Yeah, you just use the molarity formula. So molarity equals moles over liters. So I will give you guys a minute. See if you guys can calculate how many moles of KMnO4 were added. Okay, so first thing you want to do is use the molarity formula to find how many moles of KMnO4 you added. So pretty easy. Moles is going to be equal to molarity times liters. And so if you take a look at the molarity is 0.135. And then you're going to multiply that by the liters, which is going to be 0.01456. That's liters and this molarity. All right. So if you guys multiply the two values together, you should get 0.00. I got 197. And that's going to be your moles of KMnO4. Everybody good with that? Okay, now, if you take a look at our equation, we don't have KMnO4, right? But we know that if we have KMnO4, this is a salt, right? Because we got positive K plus and we have MnO4. So that means that KMnO4 is going to break down into MnO4 minus and K plus. So if we have this as our value of KMnO4 added, that means we can also infer that there are 0.00197, the same number moles of just the MnO4 minus. Okay, everybody good with that? Okay, because this breaks down into one of that. So you get one of each.
Yeah, I thought you said 50.
Oh, no. Okay, now we can use our balanced equation to convert MnO4 into C2O4 2 minus, right? Because we got both of these in our combined reaction. So we're going to get 0.00197 moles of MnO4. Okay, and then we're just going to write a mole ratio where we turn MnO4 minus into C2O4 2 minus. So if we take a look at our combined reaction that we wrote earlier, what is the mole ratio between the two?
5/2.
Yeah, 5/2. You got 5 moles in front of this guy in your complete reaction, and then you got 2 in front of this guy. So it'll be 5/2. Okay. And so for that, I got 0.00493 moles of C2O4 2 minus. So far, so good, guys? Okay, so if we go back and put this number in, that means that inside of this flask originally, we have 0.00493 moles of C2O4 2 minus. Okay, and then the question is asking, what is the concentration? So we're looking for molarity. So how do we find molarity using these two numbers? Yeah, just divide, right? Molarity equation. Molarity is moles 0.00493 moles divided by the volume, which is 0.05 liters. And that's going to get you a final answer of 0.0986 molarity. That's it. Yes.
I think you said that oxidation probably used a lot of the AP test.
Huh?
I thought you said that there was a ton of oxidation.
There is.
But you said electrochem was only like,
Yeah, very small component. So they'll include it into like solutions and things like that.
what is oxidation? Electrochem?
It is. It's the foundation for electrochem. So electrochem is like, the percentages are online. I forgot off the top of my head, but it's a component, smaller component of the AP test, but they put redox into a lot of other different things. And sometimes you'll even get MCQ questions saying like, what's the oxidation number for this element? Yeah, things like that.
Oh.
Yeah. It's like, you don't have a lot of like pure stoichiometry problems on the AP test, but like dimensional analysis is everywhere. It can same thing, same concepts.
Yeah.
Yeah.
And then what did the football dude? You like, I know you pulled up those like
Yeah.
unit things.
Yeah.
He just did all those.
He did like everything. Yeah.
Okay.
Yeah. All right. Any questions? Hopefully it's not too bad. Okay. Let's go on to the next part. Okay, so we're gonna go on to the next thing, and this is gonna be reduction potentials. Now, remember how when we talked about thermochemistry, we talked about there is heat that is released whenever we do some kind of reaction, right? Change in enthalpy. Okay, this is very similar. So these reactions also have something called electrical potential or voltage. So it's very similar in that you got a reaction, you're gonna have electrical potential associated with it. Okay, but it's going to be a little bit different, and I'll explain the reasons why. So first, just to clarify, you will always be given these numbers. You do not need to memorize any of these, okay? I'll be honest, I literally know 0 of them, okay? And I turned out fine. So you'll always be given, or maybe not too fine, but you'll always be given these values, okay? Okay, the key thing you guys need to know here is that potentials are always, and write this down, highlight it, get it tattooed on your partner's forehead, but the potentials are always given as reduction half reactions, okay? This is super important because we're gonna have to flip these reactions later, but just keep in mind, they are always given to you originally as reduction half reactions. And we know that because the electrons are on the reactant side for all of these, okay? So keep that in mind. They're always reduction half potentials. So when you try to combine 2 of these together, you're going to have to flip one of them so you can get oxidation reduction, okay? Now, it's similar to enthalpy in the sense that if you flip it, so if you guys take a look here, the electrical potential for this reaction right here is negative 0.76, right? And then if you flip it down here, it turns into positive. Okay, so make sure you jot that down somewhere as well. When you flip the half reaction, okay, you're going to multiply, or I'll just write negative the electrical potential. Okay, so similar to enthalpy, if you flip a half reaction, you have to multiply the electrical potential by negative. So that's the part that's similar to enthalpy. All right, so far so good, guys? Okay, now the reason why we talk about these is because a lot of times for these types of problems, you'll be given two different half reactions. So let me give you guys an example, and I want you guys to copy this down on your paper. But let's say, for example, let's take the two that we have right here. Let's take this one, and we got this one, okay? You see how they both have a different half reaction or electrical potential, right? They're basically going to ask you, they're going to give you these two, and then they'll ask you, okay, which compound is most likely to be reduced if you have these two reactions. So let's say they give you these two. They'll ask you which one is more likely to be reduced, Zn or F. And that's the type of question that you'll get. It might be the other way, which one is more likely to get oxidized, but it's pretty much asking you which one is more likely to get reduced. Okay, that's the kind of question you'll get. Okay, and the answer is actually pretty easy. Okay, now this is one that's also very important and worth tattooing on your partner's face. It's whatever has the larger potential. The larger the potential, the bigger, the more positive the number is, the more positive this number is, the more likely it is to happen. Okay, and that's it. That's the key. Yeah.
Even though fluorine like really hugs onto its electrons.
Yeah. Or it doesn't have to do with that so much. It's about the charge moving. Yeah. Okay, so just keep that in mind. You want to make sure you set it up so that you have a more positive electrical potential. Yes.
It's the same thing for oxidation. Will there be like a voltage for
No, you just want to make sure that this E value is as positive as you can get it. Whichever one is most positive is the one likely to happen. Okay. So I'm gonna show you guys what that means. So let's do a quick example right here with the two reactions that you have. Okay, so on your paper, I want you guys to write this down. We'll do kind of like a mini problem just so I can show you guys what it looks like. Okay, so let's write our two reaction. We have Zn2 plus 2E minus, and that's going to be Zn solid. And then the electrical potential here is negative 0.76 volts. So it was that one. And then the other one is F2 plus 2E minus 2F minus. And then the electrical potential is plus 2.87 volts. Okay. All right, so if we take a look at these, both of these are reduction, right? So what we have to do is we need to flip one of them, okay? Because when you have a reaction, it needs to be, one of them has to be reduction, one of them has to be oxidation. So the question here becomes, which one do you flip? Yeah, so it's the one that's less likely to happen, but let's talk about why. So let's say for our case, we want to make the most positive E value. Okay, so if we combine these two reactions together, we're going to add these two numbers up. Which one should we flip to get the most positive number? Yeah, the zinc one, because if we flip the zinc one, what do we get? We get zinc Zn2 plus 2E minus, and then what do we do with the electrical potential? It becomes positive. And so adding this with F2 plus 2E minus, and then 2F minus. And this one, we don't need to flip. Okay, adding these two numbers will create the most positive number, right? Get 3.5, right? Around there. But let's say that we flipped F2. This would become a negative 2.87, and then we'll get negative 3.5, right? So that's going to be a less positive number, so that's unlikely to happen. That's thermodynamically unfavorable. And so that's why here, which one do you want to flip? You want to flip this one. Okay. And so the question, if the question was which one is more likely to get reduced, we would write F2 gets reduced. And then the reason why is because you get the most positive electrical potential when F2 is reduced. Okay. And then you would say that Zn gets oxidized. Okay. That's pretty much how it goes. Okay, so let's talk about some ways this is different from the enthalpy. Okay. Okay. So first things first, we already talked about this. You want to add the potentials together. The way that it's different from enthalpy is you never multiply the potential by the coefficient. So when you're balancing it, let's say you wanted to take this. So let's say you have this reaction right here. Let's say you wanted to double it, right? To make it 2Li, 2Li plus, and 2E minus. Usually we would multiply the electrical potential or the number by 2, right? For electrical potential, you do not multiply it by 2. Even if you do times 100, the electrical potential will stay the same. Okay, so just keep that in mind. You never multiply the potential by the coefficient. Yes.
So there's not gonna be a problem like an enthalpy where it gives you the kilojoules per mole, and then it gives you a reaction.
They might.
But
They
it'll be constant.
Yeah, the electrical potential is constant. Enthalpy will change, but this one doesn't. And to my knowledge, off the top of my head, I think this is the only one it'll stay constant. All right, so this actually is the foundation for what we'll be talking about for the rest of the unit. So the big part of this unit is questions that look something like this. Okay, so let me kind of make some space right here and I'll show you guys what it looks like. Okay, so the big types of questions you'll get for this unit, and the big concept is they'll give you like a solution. Okay, they'll give you two solutions and you'll have to compare them. Okay, so let's say that in our first solution, you have a piece of solid metal. So let's say we have solid zinc, okay? And then you'll have a different metal ion floating around, like Ag, so like silver, okay? So this is solution 1, and then they'll give you the opposite solution in solution 2. Okay, so they'll give you solid Ag right here, and then zinc that's aqueous. You guys see the difference? Okay, it's pretty much just flipped. And then the question that they will ask you in the problem, they'll be like in solution 1. Okay, will Ag plus solidify? Solidify. And then the other option will be in solution 2, will Zn2 plus solidify? So basically they're asking you which one of these solutions, or like in this one, will Ag become solid as Zn becomes aqueous, or will solution 2 happen? It's basically asking which of these scenarios is going to happen. Okay, which one is going to solidify and which one is going to become aqueous? Because in one of these solutions, there's going to be no reaction. Okay, and that's always going to be the case. In one of the solutions, there will be no reaction. And that's all going to depend on the electrical potential. Yes.
So in one, the half reaction is Ag getting reduced and Cn getting oxidized together.
Yeah, pretty much. That's what it's asking. Okay, so basically you're looking for which one of these is going to have no reaction. And that's all going to depend on the electrical potential. All right. I know that seems kind of scary, but you guys already learned all the skills to do it. So let's go into a problem like that. Perfect. This is exactly what we got. So first thing I want you guys to do is I want you guys to take a look at the complete reaction. We got this right here. Oh, hold up. Let me make it a little easier for you. It's very solid. Okay, so this is the complete reaction. And then you have the two half reactions, including the electrical potential. Now, lucky for us, it tells us which one is oxidized and which one is reduced. Okay, so first one right here, part A. Will placing solid zinc into a solution containing Ag plus ions produce solid Ag? And we got to justify our answer. Okay. Now, we can answer both of these questions at the same time by looking at the half reaction. Okay, so let's take a look at the half reactions. Now, if you guys remember, what does the electrical potential want to be?
Really positive.
Yeah, really positive. So electrical potential wants to be as positive as possible. It wants to be the most positive number that it can be. Okay, that's the controlling idea for this problem, okay? You want the electrical potential when you combine these two numbers together for the half reactions, we want it to be as positive as possible. All right. So with that being said, let's look at scenario A. Scenario A is asking if you have a solution of Ag plus, okay? And you put a piece of solid zinc in there. Is it going to produce solid Ag? Okay, so this actually tells us what kind of chemical reaction we're going to get. So if you take a look at part A, if we're going to write a chemical reaction for part A, what would be your two reactants?
Ag and zinc.
It's Ag and zinc, but what's the state of matter? What's the state of matter for zinc? What are you starting?
Solid.
Yeah, so you're starting with solid zinc. So it's basically asking you if you have solid zinc and you're combining it with Ag ions, so plus Ag plus, and this is aqueous. Is it going to produce solid Ag? And if one of them solidifies, the other one needs to ionize, right? So it's basically asking here, is this reaction going to happen? Okay, is this going to happen right here? Okay, so let's take a look at the oxidation and reduction reactions. Now, do we need to flip either of these to make this reaction right here?
No.
No, we don't, because we got Zn plus or Zn solid on the reactant side. We got Zn2 plus on the product side. The electrons will cancel out. Ag plus on the reactant side. Solid Ag on the product side. So this is exactly the way it should be. So let me give you guys about 30 seconds. See if you guys can calculate the electrical potential for the reaction that they're proposing in part A. Yeah. Huh? So we want to flip it when they don't give, because this one was being nice. It gave you the reduction oxidation one. Remember how usually they gave it in reduction? So they would usually give it flipped already. So it'd be Zn2 plus 2E minus makes Zn solid. And then that's when the electrical potential is negative 0.76. So if they weren't being nice and you had this, you would have to flip it to make it positive. But they already tell you it's oxidation reduction. So you didn't need a flip. Okay. Does that answer your question? Yeah, you only want to flip it when you're trying to make the reaction they're asking for. But here, luckily, we don't need to. It's already the reaction they're asking for, so you can just add it together. Yeah. Yeah, only flip one of them. Or actually, both of them if you need to. But... All right, guys. So for the electrical potential, it's just 0.76 plus 0.8. So that's going to be positive 1.56. Okay. And it's volts. Yeah.
Well, for zinc being positive, will Ag always be negative? Like I said, will there be an instance where both the oxidation of silver and the oxidation of
Yeah, there's a chance that you can have two reactions that are both negative, both positive.
so then in that case, which one's more positive?
Yeah, so you got to figure out which one to flip. This one already kind of did the work for us for that part, but usually, maybe I might change this question, but it should give it to you in reduction. So this should have been negative 0.76. And the key is to figure out that you need to flip this one. Okay, so that's part A. Before we figure out which reaction to do, let's look at part B. Now, for part B, what are the two reactants that they are proposing here?
Solid Ag and zinc.
Solid Ag and zinc 2+. So here they're asking, can you get solid Ag and zinc 2+, and then can you produce solid zinc? And obviously then the Ag will have to ionize out. Okay, now, in order to find the electrical potential for this one, what do we have to do with the half reactions? We have to flip both of them, right? Because we need to get solid zinc onto the product side. We need to get solid Ag on the reactant side. So if we flip both of them, you're going to get negative 0.76 plus negative 0.8. And that's going to give you, negative 1.56 volts. Okay, so that's the electrical potential when this reaction happens. And then the electrical potential for this reaction is positive 1.56. So which one of these reactions is going to happen, A or B? Yeah, A is going to happen. Why is A going to happen? Yeah, this happens because it's a more positive electrical potential. Okay, so this is the one that happens because it has a more positive electrical potential. This one does not want to happen because the electrical potential is lower than the alternative. Okay, so this is what is going to happen. So if you put a piece of zinc inside a solution with Ag ions, you will produce solid Ag and the zinc will ionize out. All right, and that's it. That's for that's how you can figure out which one plates out. Yeah.
So it's kind of just like delta G, but like
Yeah, with given reactions, pretty much. Yeah. Okay, so the most important part of electrochem, and the question that is most likely to be on FRQ is going to be about this thing right here. It's called a galvanic cell. Okay, I hate the galvanic cell. Number one, it's a lot of components to it. Number two, I hate electrochem. Number three, my English teacher in 10th grade was Miss Galvan, and I really did not like her. So when I saw this, I hated it even more. Okay, shout out to Miss Galvan, okay? All right. So a galvanic cell is basically how a battery works. So did you guys ever watch Breaking Bad? Do you guys know or if you didn't, there's an episode where Walter White and Jesse, they get stuck in the desert, right?
yeah.
And then because the car runs out of battery, and so they make a battery, a liquid battery. Dude, you participate so much when we talk about these dumb things. But yeah, basically they get pieces of metal and they make a liquid battery. Basically, they make a galvanic cell. So let's talk about how a galvanic cell works. Okay, do you guys have this picture on your Chromebooks? Okay, so if you don't, I recommend having it. But a galvanic cell works because of a redox reaction. Remember in the previous problem, we talked about how one of the redox reactions is preferred, right? It's thermodynamically favorable. Now, basically a galvanic cell works by taking a redox reaction that is thermodynamically favorable, that has a positive electrical potential, okay? So we're going to talk about the different components, yeah. It's always going to be positive. Electrical potential is positive. Okay, so on your papers, I want you guys to draw this because I'm going to show you guys how a galvanic cell works. Make sure you make it a decent size because we are going to be drawing on your galvanic cell. Okay. Okay. So a galvanic cell works with two components. Okay. There is going to be one container here and another container right. Oh my gosh, I cannot draw a straight line. Dude, I just literally developed arthritis within 10 seconds. All right. So we got two galvanic cells, or we got two solutions, okay? So on one side, you're going to have a solution, and on the other side, you're going to have another solution. Okay? Again, we're going to be labeling this, so just make sure you make it a decent size. Yes. What giant pointer? Oh, I made the other one work, the one that I like. I hate that giant pointer. No, it was a software update. Yeah, bug. All right. Now, one of the sides is going to be positive and the other side is negative. Okay, so let's make this side the negative side. Okay, this is negative. And since it is negative, we call this the anode. Remember, cations versus anions? Same thing. The negative solution is going to be an anode, and this right here is going to be the cathode. Okay, so the cathode, what happens here is reduction. You do need to memorize this. The cathode is where reduction takes place. The anode is where oxidation takes place. Okay. Everybody good? All right. Now, when you have oxidation, what happens in oxidation? What happens to the electrons? It becomes more positive and electrons are lost, right? So that's basically how it works. What you do is you get a little wire usually, or you're going to have two metals. So here we're going to have a metal. So let's draw a metal stick. This metal. And you're going to get another metal right here. And they're going to be connected with a wire. Okay. And basically what happens is, since this is oxidation, electrons are lost, right? So the electrons are going to leave the anode and they're going to travel along the wire and into the cathode. Okay, so this is the direction of the electrons. Just remember, oxidation, electrons are lost. And then reduction, electrons are gained. And so the anode loses electrons and goes into the cathode. Yeah. I don't know. Ask your cousins, dude. Somebody in Europe probably came up with this. I'm sure there's a reason why. I don't know. Okay. So far, so good, guys. The anode loses electrons to the cathode. Okay, now we do need to compare. Oh, so because this happens, there's going to be an electrical current. And so usually in between, there's something called a voltmeter. And this basically measures the electrical potential. Okay. This measures the volts. Okay, but basically this is the premise. Electrons move from the anode into the cathode. However, if you guys took physics, you should know that in order for there to be electrical current, you need to complete the current. So in between the cathode and anode, there is one last thing. And that thing is going to be something called a salt bridge. And so basically it's a piece of salt that connects it. And we'll talk about what the salt bridge does in a second, but this is your salt bridge. It is basically a piece of salt, okay, that connects the two. And that's pretty much what a galvanic cell is. Now we're going to talk about what happens more specifically in that, but that's a general principle. Do you guys have any questions so far? Okay, because you're going to have a question like this on your test, guaranteed. And high likelihood this year, we're going to have a question like this on the AP test. Okay. So I'm going to erase the voltmeter because that's the least important part right here. Okay, but let's talk about how this works. So Basically your anode is going to be made of some type of metal. Okay, so let's say, for example, this right here is zinc metal. So let's label it zinc. And so here we have a piece of solid zinc. That's what this metal bar is. Okay, this metal bar is solid zinc. Okay, and then let's say that here at the cathode we have a piece of copper. Okay, so we have solid copper. Okay, so let's say those are the two metals that we're working with. We got zinc and copper. Now, what happens at the anode is there's going to be zinc ions, so the same metal ions inside of that solution. And this is what happens at the anode. Basically, the solid is going to break down. It's going to ionize into the ion. Okay, so let's jot that down somewhere. In the anode, the solid metal, or I'm going to write solid zinc ionizes into the solution. Okay, which makes sense, right? Because if it goes from zinc, which is 0, to +2, this thing is losing electrons, right? So as it ionizes, it loses electrons, and then that's how the electrons are able to move to the other side. So that's what happens at the cathode, or sorry, anode. All right, make sense? At the anode, the solid turns into aqueous ions. Okay, now, as the electrons move from the wire to the cathode, what's going to happen is the solid copper right here, okay, is going to get electrons, right? And so there's going to be copper ions in the solution. And what's going to happen is the reverse. The ionic copper is going to solidify into the solid copper. So here, the ionic Cu2 plus solidifies into solid copper. So it's basically opposite things happening. In the anode, the solid metal turns into ions, and then in the cathode, the ions turn into solid metal. Okay, so if we actually made a galvanic cell here, you would see over time that this piece of zinc would actually get smaller and smaller, and this piece of copper will get bigger and bigger because one side is losing ions, one side is gaining the solid. Yeah. Exactly. They're forming, yeah. You'll see like later. I'll show you a picture in a second, but that's exactly what happens. Yeah.
So it was a lemon battery technically to galvanic cell.
No, because you need these metals for the cathode and anode. Yeah.
No, what if you say zinc and copper and the lemon?
Yeah, that could work then. Yeah. Yeah. All right. Any questions? Okay, we're almost done. We have one last component, and that's the salt bridge. Okay, the salt bridge is made out of obviously a salt. So here, let's say, for example, we have KCl. Okay. All right, now, let's take a look at the anode. If we're getting more Zn plus here, what's happening to the solution as the reaction goes through? Is it becoming more positive or more negative? The solution becomes more positive. So to balance that out, what's going to happen is, you see how the salt bridge is made out of K and Cl, right? We know that's K plus and Cl minus. What's going to happen is the salt bridge is going to pretty much send Cl minus ions into the solution as the Zn2 plus goes into the salt bridge to make make the salt. So here, opposites are pretty much going to attract. The Zn is going to go into the salt bridge, and the Cl minus is going to also meet the Zn2 plus. And you can pretty much assume the same thing right here. Here, we got Cu2 plus, and usually there's another ionic salt in here. Let's just say it's SO42 minus. Okay, whatever was bonded to the Cu. This one is going to go into the salt bridge. And then here, the K is going to leave the salt bridge. Yeah.
So it's not just copper that's going there, it's copper.
Yeah, you're going to need some other thing in there. So
Is that only for the cathode or?
for both. So let's just assume that it's gonna be, you're gonna want the same, what is it? The same anion. So Zn SO4 and Cu SO4, like that. That's it. So basically the Zn is gonna lose, the solution is gonna lose Zn2 plus, and you'll have more SO4 2 minus. That's why this becomes negative. Here, you're gonna lose SO4 2 minus and get more Cu2 plus. So that's, this side becomes positive. Okay, but that's it. That's pretty much how a galvanic cell works. Okay, two components, and then there, you got two connections between. Water ion with a salt in there. It's a salt solution. So this side will be in a Zn2 plus solution, or sorry, ZnSO4 solution. This side will be in a CuSO4 solution. And so, like I said, the Zn is going to disappear and you're going to get more Cu. So I have a pic, I'll put that picture back up. But if you actually ran a galvanic cell, this is how it would look at as the reaction progresses. The Zn will start to disappear, whereas the Cu, you get more of it as the reaction takes place. Okay. But that's it. That is a galvanic cell. We'll do more problems with that later. But do you guys have any questions on how it works? Yeah.
So where does the Cu go? Where did the Cu come from that went into the metal?
Oh, you have a CuSO4 solution already.
Oh, okay, I thought it
Yeah.
was
Oh, no. You need a salt solution in there. Yeah. Any type of Cu salt solution.
And do you have to like or is it just making electricity on its own, or does something have to like catalyze?
You just need to connect them together.
Okay.
Yeah. So if you, and I think Breaking Bad did a great job showing it. Basically, they made like a couple buckets like this, and then they had a salt solution. They put the metal into both of them, and that's what creates the current. Eventually, you'll run out of current once the reaction is finished. But yeah, that's how it works.